Thank you so much, everyone, for coming today. My name is Thomas Joshi. I'm co-author of Stanford DSPy. If you have any questions after today's talk or you just want to stay in touch with me, you can go to bit.ly/DSPy help, drop your email, and I'll be giving you updates. Or if you just have questions, just let me know. Or you can connect with me on Twitter at Thomas T. Joshi. And so today we'll be talking about how we can actually get started applying DSPy in real-world problems. So today's talk really deals with one of the problems I have, is that I'm tired of people saying that LMs have no real utility. So this will be one of the most actionable talks at this conference. I'm not going to go in depth of explaining DSPy. There are a lot of YouTube tutorials online that explain the underlying concepts, but I'll give you just enough to bridge the gap between academia and enterprises, and then we'll move with a sense of urgency through case study after case study so that you can get intuition. And then you'll realize that LLM systems are actually here. Deploying LLMs is as much as about problem engineering as it is much about a AI engineering or AI research problem. And instead of saying, we'll put up chatbots everywhere, if you can be thoughtful about the types of problems that lends itself to an LLM, then you can really start delivering value for your customers and employees. Now, you still have to do the hard work of ensuring proper guardrails for your DSPy system, ensuring customer data privacy, and identifying problems where that lends itself to the LLM system. But if you can do this, you will start developing intuition for AI with a human in the loop, or your own use cases that lends itself to the DSPy system. So you'll be bursting with ideas after we walk through these case studies. But first, let's walk through what's ahead of us. A little taste for the presentation. A multinational bank is testing DSPy to streamline the client onboarding process and enhance the risk assessments. So during the client onboarding process, each client completes a risk assessment form, managing financial risks through the completion of this form. So traditionally, human quality checkers would review these assessments, identify these sources of funds, and then give feedback in terms of what are the sources of funds here, reasoning for that. And so these human quality checkers, they have to go through many of these assessments, and they could potentially make a mistake. Now, with DSPy, you can enhance this process by equipping the human reviewers with advanced tools to more efficiently identify errors and then generate precise explanations behind those errors. And so this is not full automation. This is AI with a human in the loop. And so with that comes with real results that you can deliver today, not in 10 years from now when we have AGI. So if you can assist human reviewers, you can speed up the human resolution process and enhance overall accuracy. DSPy chatbots are being built to support JetBlue's operations by leveraging real-time customer messages to swiftly identify and address in-flight entertainment issues, enhancing the passenger experience. In airport environments, DSPy can aid in monitoring PA systems by analyzing feedback, ensuring timely maintenance and updates to enhance communication. For JetBlue employees, DSPy can streamline access to payroll information, enabling quick and accurate responses to HR inquiries, leveraging RAG, and thus improving employee satisfaction and operational efficiency. So that's just a little taste of what DSPy can do. Then this is a high-level overview of what we'll cover today. We'll quickly go through the problem. We'll spend a little bit of time on these brittle language model pipelines, prompt engineering, and these are a nemesis. The solution is DSPy conquers these enemies through borrowing concepts from PyTorch to create these three fundamental building blocks that any engineer or any enterprise can adopt. So then we'll apply these building blocks to three different industries. So in finance, we dive deeper into the risk assessment example I provided earlier, and you can use DSPy for these risk assessment forms. Then we'll go into cybersecurity. We'll talk about Hays Teams, which is using DSPy for red teaming their LLMs. We'll go into healthcare. DSPy systems are astonishingly good at detecting and correcting medical errors and medical notes. And then finally, I'll wrap up with settling a debate. So I'm sure you've all seen on Reddit or on Hacker News, should I use DSPy, should I use LangChain, should I use Llama Index? We'll put that debate to rest. And those discussions are kind of absurd because many of you are already using Llama Index, and Llama Index is great at a few things, and DSPy has its own specializations. And so you'll have a deeper understanding of how to integrate some of these modern tooling systems today. So let's first go into the problem. And the problem goes straight to the core of language models themselves. Training costs are skyrocketing, not even accounting for the people required, data gathering, the inference costs. And according to scaling laws, that shows us that given a compute is becoming more cost effective to train a smaller parameter model with more data versus some state-of-the-art model. The order of magnitude of scaling, the power required, the number of GPUs necessary, the size of the model, this is all rapidly increasing. And so I know we have new hardware coming, and I know there's a number of people working on this problem, but we still need systems that can take smaller, cheaper, more nimble models that we currently have and find a way to leverage them to optimize results. Another problem we're dealing with. So hopefully no one in this room is using sort of single model chatbots, and we've graduated from using that. A significant limitation of single model chatbots is that they struggle to decompose complex problems into manageable subtasks. So they don't have proper context. So consider a real-world scenario. So a user is delayed by traffic and inquires that their flight is on time, expressing a desire to get home quickly to their kids. Well, the user's statements involves multiple layers. This traffic delay, the flight schedules, the logistical information. So due to their design, the logistical information is embedded with the flight information. And so that whole emotional context needs to be broken apart, and then you need to find the relevant information in your system. Now, maybe some of you have graduated to a RAG-based system. Building on our understanding of the single model chatbots, we have this introduction of a retrieval model, which marks a pivotal enhancement. The retrieval model retrieves information that augments the language model's responses, and so that ensures answers both relevant and accurate. But while this RAG system enhances the response quality by integrating relevant data, it also introduces a level of complexity and potential brittleness and akin to earlier rule-based systems that we saw that were developed going back to the 1990s, even earlier than that. So while pipelines offer great potential, crafting them effectively is quite challenging. Firstly, figuring out how to seamlessly connect and optimize every element of a pipeline can be elusive. And in addition, prompts using these pipelines tend to be very delicate and don't easily adapt across different applications throughout your enterprise. So as you can see, while pipelines are promising, if you're an engineer building out these pipelines, you want to set yourself up for success later down the road. Now, when these foundation models change, the retrieval model may change, these pipelines need to be robust to those changes. And AI researchers and engineers should focus their expertise on innovation rather than spending their time handwriting prompts. With the rapid pace of advancement in AI, the models like GPT-3 and DBRX, these will be frequently upgraded and they'll be replaced, requiring prompt adjustments. So tools like DSPy are essential because they automate prompt adjustments by reducing the time and effort needed for manual updates. Now, this automation not only streamlines development, but also allows researchers to focus their time on things that are critical, innovative tasks in AI development, things that are actually useful to your customers. Okay, so now we will go into describing a quick high-level overview of DSPy. So DSPy harnesses familiar concepts to construct sophisticated, adaptive language models. It provides essential building blocks and a compiler, so you can focus on application-level development rather than these low-level details. So DSPy is analogous to PyTorch, and that's on purpose. So instead of dealing with tensors, DSPy operates with text. Instead of dealing with individual neural layers, it interacts with whole language models. So DSPy allows engineers to work with a familiar framework, and that allows you to minimize your learning curve and accelerates the deployment for your team. So the core of DSPy is setting a new standard in AI development with our core foundation language model pipeline components: the module, the optimizer, and the signature. Modules are like your engine of your LLM system. You're architecting the bedrock of your future automated systems throughout your organization because those LLM pipelines can be reused. Like layers in PyTorch, this module behaves as a callable function. So we bring in keyword arguments, and then we format a prompt to implement the input. We include the appropriate demonstrations and call the LM, and then parse the output. Signatures are where we refine our input fuel and the output. we define what input and what output does our LLM system going to take. Now, optimizers. So they take your DSPy program for an upgrade, ensuring peak performance, allowing it to adapt to new challenges. Recall in PyTorch, we had Atom and AdaGrad optimizers. Well, now this next generation of optimizers will introduce a suite of optimizers for your LLM pipeline. And that's all you need to know for now, and you'll learn as we go through these examples. So the first example is in finance. So first of all, we need to identify where this new client is coming from, right? So remember the problem. We have this risk assessment form, we onboard a client for a financial institution. So DSPy gets a summary from the human analyst, describing the client and the human analyst identification of the source of funds. Then you've got two straightforward tasks for the DSPy system. Task 1 involves identifying each risk assessment form with the correct source of funds. And then that can be business activities or third parties. Task 2 takes it further by generating a detailed explanation for any discrepancies or missing information regarding fund sources. That enhances transparency and compliance for the financial institution. So at the bottom here, we have an example of our input. The client operates a software company. They maintain a cloud computing platform and sells that access to customers. And this generation of income comes from that platform, but they also generate funds from venture capital. So we are combining an analytical AI problem of classification with a generative AI problem of explanation. And when you're looking to apply DSPy, this is a very highly recommended pattern for how to apply DSPy. It's simple, it's straightforward, it uses familiar concepts like classification that we've seen from machine learning, and it can deliver real results. This is particularly useful if you work at a large company which has a large staff processing large amounts of administrative documents. Leverage that staff as an entry point to deploy your AI system. Go to the key stakeholder, and instead of promising to automate all their work and replacing them, promise to make their life better. Ask them what key metrics matter to them. Turnaround time, error detection. Ask yourself how you can get this person promoted instead of automating them out of their job. And if you can do that, you can start to get a foothold in your enterprises, in your organizations, to implement DSPy. And if you have any questions on that, please let me know. As I alluded to, I left the document and my Twitter handle. Okay, the first step in any DSPy program to build this risk assessment pipeline is to define your input and output to your modules. So in this toy example, we have two sources of funds. I create signatures for determining if the client's source of funds is business activities, and perhaps that's relating to selling goods or services. And I create an input field called summary and an output field called yes, that outputs yes or no. I create a signature for identifying third-party sources of funds. So the third party represents maybe you have a venture capitalist or a lender who's giving you that capital. So once again, create the input and output field. But to use a signature, we must create a module with that signature. Okay, let's first create the source of funds analyst module. This module is configured to predict and classify a client's risk assessment form and identify their source of funds. So in part 1, we define our constructor. I create our self.predict business activity and predict third party by passing our signature to predict. So what is predict? And now I'll give you a little bit more conceptual understanding of DSPy. That's our core module for working with signatures in DSPy. So DSPy includes a number of more sophisticated modules like chain of thought and React. I'm sure you'll recognize these names from papers. And so we try to stay with things that you're familiar with. So recognize the second method, it's called forward, right? So if you're familiar with PyTorch, that sounds very familiar. And so this is a very easy learning curve. The forward method takes in that summary from the human analyst, describing the client. It takes in the source of funds, identified by the human analyst. It then goes through our classifiers, determining the DSPy system's take on what the source of funds are. Part 2 introduces an initial DSPy feature, suggestions. And that allows you to debug your DSPy system like you would a normal software system. So we have a forward method. We have a modular way of defining our code base. We have ways to debug our system. And then you pass that to your optimizer. So it takes the program, a training set, and a metric, and returns a new optimized program. And metrics can be simple notions like exact match, but they can also be more complex DSPy programs. So this training set doesn't have to be n equals 100. It can be small. It can be 5 or 10 and incomplete. Only inputs to your program without any labels. So this labeling efficiency is where the power is, because that maintains the modularity. Building a new pipeline DSPy requires simply recompiling that new pipeline, not annotating data specific to a new pipeline. Okay, so now what you might be wondering, and I get every single time I get to this part in the presentation, which is, how does it optimize my program? What's under the hood? Well, it depends on which optimizer you use. So another layer of concepts for you as we go along here. Let's take an aside to study these. So in PyTorch, remember, we have those optimizers. Well, we have our own class of optimizers in DSPy. With DSPy, you can tweak examples that are fed into the prompt. So we have Bootstrap FewShot. That's a class that composes a set of high-quality demos to go into that prompt. These demos come from a combination of labeled examples in the training set and bootstrapped examples. And it uses a teacher module, which defaults to your program, to generate those complete demonstrations. So bootstrapping process employs the metric to validate demonstrations and includes only those metrics that pass the metric in the compiled prompt. We also have a little bit simpler optimizer labeled FewShot. So that requires a certain number of examples for the prompt and train set to randomly select k examples from. We have Bootstrap FewShot with random search. So that applies Bootstrap FewShot, but now we'll use random search over our generated demonstrations. We have k-nearest neighbors FewShot, which selects demonstrations through k-nearest neighbor algorithm. And so if you have a computer science background, you'll recognize random search, k-nearest neighbors. These are words and concepts that are familiar to you. So again, the optimizers are designed so that it can be easy to adopt. And finally, if you look through online tutorials, you often see MyPro. This is a different class of optimizers. So the past optimizers belong to a class of optimizers which we'll call FewShot Learning. Now, MyPro is part of a class of optimizers called instruction optimizers. So MyPro generates instructions and FewShot examples in each step, uses Bayesian optimization to search over the space of generation instructions and demonstrations across modules. And so the more demonstrations you have, the more likely you'll use a more advanced optimizer like MyPro. And we've covered now signatures, modules, optimizers, and what they typically look like. But we aren't done yet. We've created a module that classifies our risk assessment form, but we can't operate LM systems like black boxes. Right? This was a big complaint about deep learning systems. They get high accuracy, but we don't know what's going on like we would with a tree classifier, if you will. So at the minimum, we need to document some rationale for these classifications, and LM systems need to effectively communicate to a human analyst, and then also when we go back and we audit our systems, we need some explanation. So in order to create an explanation of our classification, we'll first create a new signature. Once again, we'll define our inputs to be a risk assessment form and labels that were identified as missing in order to output a review. And we'll call that signature quality commentary. We'll provide this prompt, which we don't need to worry about continually updating, and we'll tell the system to take the risk assessment, determine why the labels are missing, and we want to use LLM as a reasoning engine now. So you might have said with the prior example, okay, who cares? It's a classifier. I've always been doing that for decades. Well, let's start using the current state of LLMs as a reasoning engine. We now build our module using the quality commentary input-output definition, and in the constructor, we'll pass the quality commentary signature to predict. We have our automated analyst ready to go determining what funds are missing, and then we generate a comment for the human reviewer. We pass this program to DSPy to optimize the prompt and system. And as a reminder of our original task, the risk assessment talks about a client. They own the software company. They generate money through the profits of their cloud computing platform, and they also raise money through VC. So let's identify the client source of funds. At the bottom, you see what the DSPy system predicted, and what the human predicted as input labels. And finally, you see the DSPy quality analyst explaining to the human analyst why they were mistaken. Now, imagine you are someone who has to spend hours every day of their lives going through hundreds of these reports. If you have to go through one, maybe you can do that on your own. But this tool is a lifesaver, because before we had spell checkers, This is a workflow checker. And so it completely revolutionizes our administrative functions, and the potential is limitless. Okay, so what are the key lessons from this example? When you're developing compound AI systems, it's all about problem engineering. Don't make the excuse that you need to get to 99% accuracy. Some problems, especially in administrative functions, just need to be helpful more times than they're wrong. And so you need to identify workflows within your organization, decompose those workflows into specific subtasks, create modular solutions with DSPy to address those subtasks, and you can use those modular solutions throughout your organizations because those pipelines will be reusable throughout different common workflows. And then optimize your demonstrations using our suite of optimizers. Now, we'll go into another area, cybersecurity. Hays Labs has developed a fascinating approach to automating red teaming, addressing the challenge of searching the vast language space for adversarial prompts. So red teaming LLMs, if anyone doesn't know, it involves simulating adversarial prompts and attacking the model to test their resilience and identify vulnerabilities. Now, this process helps improve the model's robustness against potential misuse and enhances overall security and reliability in the real-world scenarios. The DSPy optimizer called MyPro, combined with a language model, acting as a judge, refines strategies for adversarial attacks and making it an effective tool for testing AI robustness. Hays Labs has defined the success of an attack using LLM Judge. So instead of before, where we might use a binary yes or no, we'll use a continuous scale to refine our approach iteratively. Once again, it all starts with a signature. Define your input and output. So they have this class designed to generate an adversarial prompt. It uses two input fields, harmful intent, the specific harmful outcome desired, and critique, the optional feedback on previous attempts. Now the output here is an attack prompt, which is a constructed phase designed to prompt another language model into producing some specified harmful intent. Then we have our second refined signature. So this is a different set of input-output pairs. This class refines that attack prompt based on the effectiveness of the initial prompt. It takes three inputs: the harmful intent, the attack prompt, and the target response. That target response is the response from the target language model. Now the output, which is the critique here, offers suggestions on how to edit the attack prompt to more effectively manipulate that target model into producing the desired harmful intent, while staying relevant to the original intent that the LM system had intended. So now note how this structure is iterative without trying to try a bunch of different structures and hiring more engineers and throwing tomatoes at the wall. We can use a refined approach that we can automate. Now let's define our module, the engine of our system. The attack program class automates adversarial testing by iteratively generating and refining attack prompts using DSPy. It constructs multiple layers to systematically attempt to exploit the vulnerabilities in a language model by simulating attacks and then refining those attacks. So each layer consists of an attack generation phase, and then that's followed by a critique phase. So we have the attack module constructor that defines a number of layers of refinement. They pass the attack signature to the predict module, so that's the most basic module we have for 5 attempts. And so they also pass the refined signature. The forward method orchestrates this process, initiating an attack, receiving the attack response, and refining. So this really exemplifies another pattern in DSPy you can utilize. Once again, we have our optimizer. The optimizer is set up with specific metrics here. We notice how we've kind of beefed up how we use our optimizer to compile the most effective attack program, iterating over 30 trials. And after compiling the best version of the attack program, they evaluate its performance against the training benchmark. Okay, let's go back to our framework here. Identify. So we have a wide search space of text that could jailbreak an LLM. We must decompose. We have a generation phase. Then we have an editing phase. Then we must attack. We have an attack module and then a refinement. Then what is our optimizer? Well, we have a little bit more data here, so we'll use the MyPro optimizer. Moving on to the next industry, healthcare. So Wing Labs has achieved first place in both tracks of the Medica 2024 Clinical NLP competition, showcasing their innovative approach for healthcare safety. So they successfully leveraged DSPy framework to optimize detection and correction of medical errors in clinical texts. So there are two data sets here. The MS dataset, which consists of a training set containing 2,000 clinical texts and a validation set containing 600 clinical texts. The MS dataset, the errors are subtle, so maybe a one word is off. And that's kind of similar to a multiple choice problem, and that kind of idea will come up later in the presentation. Then you have the UW dataset. That's a validation set containing 200 clinical texts. And so the results here, you see the test set for the shared task includes clinical text from both datasets. Let's walk through how they engineer their DSPy pipeline. So first, we must provide high-quality examples. But recall how the MS dataset typically has one word off. Well, the MedQA dataset, it's an external dataset, which is a medical question answering dataset that contains multiple choice answers, and each with a set of answer options and a correct answer. So what they do is that they beef up their DSPy system with retrieving multiple choice questions using TF-IDF to identify similar questions from the MedQA dataset. Then they employ DSPy module to generate the targeted few-shot examples, enhancing the model's ability. The model's goal is to identify the most likely answer choice directly from the query text and to improve demonstrations. And if you can combine information retrieval over that corpus with DSPy optimizers, the results start to compound. And then next, another DSPy module takes over, creating multiple examples that compare the extracted answer to the correct choice to make a judgment on whether we think there is an error here. Okay, so error detection, now localization. Let's find this error. Once you detect that there's an error, inputs are extracted answer choices and the pre-processed query text. It employs a large language model to precisely identify which line in the query contains the suspected error. And the output here is a specific line number to identify where the error is. So this target approach allows us to efficiently pinpoint and detect errors. Now let's go about doing a more generative process here. So the system begins by taking 3 key inputs for a medical error corrector: the identified error line, the extracted error answer choice, and the correct answer derived from a similar multiple choice question. It leverages these inputs to specifically target and correct errors found in clinical texts. So this system optimizes few-shot prompts, which are fine-tuned based on their performance on validation datasets, ensuring high accuracy. So this optimization process helps in refining the prompts that are more efficient at correcting and identifying those errors. Let's go back to our framework. We've identified a workflow. Medical note-taking is critical to tracking patient symptoms. We decompose our workflow: detection, localization, correction, and then we create modules to benefit those particular sub-problems. We detect, we use the module answer extractor, answer checker, error localizer, and error corrector. Now I want to go into integrations. So for the first part of the talk, I settled this debate. DSPy has real applications, it's already being used, and it's really a matter of AI problem engineering as opposed to just pure AI engineering. Well, LangChain and LlamaIndex generally help application developers who need prepackaged components and chains. So they implement popular classes, and with that comes nice tooling. LlamaIndex has a great set of text processing tools. And if you really want to build modular LLM systems, you can use DSPy in your current LlamaIndex pipeline if that's what you're using, and will also work very well with LangChain. How does that work? Well, for example, let's take some LlamaIndex code. So I have this initialized parser that I define, so that the llama parse object is created. We create and configure the index, so I have this vector store index created from the loaded documents and assigned an ID of vector index. We set up storage and load an index. So storage context is defined with a persistent directory and the index is loaded. And then we'll initialize a query engine. The index is transformed into a query engine configuring to summarize the summarized responses ready for executing queries based on those indexed documents. So now we have our data pre-processing with LlamaIndex, very useful. Now let's define our DSPy system. The process document signature defines the structure for answering questions using the DSPy, where the input fields accept context and a question, and the output field is reserved for the answer. This signature serves as the foundation for the document analyst module, which is built to handle the context and generate responses. So remember when you were first learning object-oriented programming, classes could be like nouns and the methods were like verbs. Well, here, when you're thinking about defining your modules, think about nouns, think about analysts, think about people who might have done this task in times prior. So it begins by querying the relevant data, then uses the extracted context along with the question to generate an answer. Finally, the module combines the context and the predicted answer to produce a structured response. So in order to test this system out, we'll initialize the document analyst object with an engine designed to process and analyze text, an optimizer, specifically the bootstrap few shot, set up using a metric called validate answer, and the optimizer then used to compile the document analyst with a training data set, enhancing its ability to generate accurate predictions. Finally, we use that optimized analyst to make a prediction on a given question. Okay. Today we outlined the problem and DSPy as a solution. In the finance example, we learned how to work with a human analyst in order to categorize and explain our results. In the cybersecurity example, we learned how to automate the red teaming process and use DSPy to iteratively improve systems. In the healthcare example, we learned how to detect and correct errors. Hopefully, you now have the tools to build your own systems. If you want to stay in touch with me or need help, please leave your email. My first objective to this talk is to take action. So happy to walk you through how to decompose your workflows in order to best do that. And when you were first using PyTorch, you didn't quite know, what neural network to define, right? Everything was fully connected. And that same process is happening in DSPy. You may not really know what patterns are useful right now, but over time, you'll start to get practice with this. You'll start to see common patterns that come everywhere when you're using DSPy, and you'll start to get up the learning curve. So, and once you do, you'll be a master of DSPy, and thank you so much, everyone, for coming to today's talk.